Hello, ladies and gentlemen. Today's topic of discussion in momentum and collisions is elastic and inelastic collisions. Now, this first slide asks you to rank these things from most elastic to least elastic, or so on and so forth. But what I don't like about this first slide is that it assumes you already know what inelastic and elastic collisions are. So, in an inelastic collision, when the objects collide, they stick together. Okay, so that's inelastic. When they collide, they stick. In an elastic collision, when they collide, they bounce off. Okay, so inelastic, they stick, elastic, they bounce off. So we're not going to rank these, but let's just look at which ones are going to bounce off and which ones are going to stick. So when a baseball comes in contact with a bat, the baseball is going to bounce off of the bat and fly off. That's what you're trying to do. You're trying to hit the ball as far as possible. So this would be an elastic collision. In a baseball and a glove, in that scenario, you're trying to catch the ball. So when the ball comes into the glove, you close the glove, and now they're stuck together. Okay, so that would be an inelastic collision. Two football players, usually somebody is trying to tackle the other person, so that would be inelastic. They collide and they stick together. When you're playing pool, when one ball hits another ball, they bounce off, so that would be an elastic collision. Two balls of modeling clay. Okay, I'm assuming everyone has worked with clay at some point in their life, because they use it a lot in smaller or in the younger grades, kindergarten, preschool, first, second, third, whatever. They use clay, and sometimes in science classes, but sometimes just for fun in art classes and things like that. So when you put a piece of clay with another piece of clay, it sticks together. So if you throw two balls of modeling clay at each other, they're going to stick. And then rubber balls, we all know that rubber is bouncy. Okay, you ever play wall ball? The ball is made out of rubber. Okay, or bouncy elastic material. So rubber balls are going to bounce off of one another. So it'll be an elastic collision. And then you have a car accident, an automobile collision. Now this one is more realistic in the sense that no collision is ever going to be 100% elastic and or 100% inelastic. You're always going to have a combination of both. An automobile collision, you have some elastic and inelastic properties. Obviously, when you collide, the cars are going to crumble together and they're going to stick for a little bit, but then you might get a little bit of bouncing off. So in all collisions, you're going to have a little bit of both. You're never going to have a 100% of one or the other. Okay, but now let's get a little bit into the actual content. So in an inelastic collision, two objects are going to collide and stick together. And what is most important is that momentum is conserved. Okay, this is the key part to solving these types of problems. Momentum is conserved. And obviously, if the two objects are sticking together, their masses are going to be combined. Okay, so what they're trying to show here is this m1v1 plus m2v2 is equal to the sum of both times whatever the final velocity is. What is this? Where does this come from? So this goes back again. From the very first section. This goes back to the momentum equation. Momentum is mass times velocity. So when they're saying momentum is conserved, they're saying the momentum in the beginning. The beginning would be before the collision. It is going to be the same as after the collision. So this piece right here, this piece right here, this is your initial momentum, okay? This is your momentum in the beginning before they collide. You take the mass of the first object times its velocity, and then the mass of the second object times its velocity. This will give you the initial momentum. This is initial. This is what it is in the beginning before the crash. Okay, this is initial. And again, this is sometimes hard for me to write on with this mouse, but this is your. I'm not even on a mouse. I'm actually on the pad on the laptop. So this is your initial momentum. This side is going to be your final momentum. And the reason they're adding the masses together is because the objects collide and stick together. So when they crash, now they're stuck together, which means the mass, if you change that to M3, let's say this is M3, M3 would be the same as M1 plus M2. Okay? So this is your final momentum. So your momentum in the beginning has to be the same as your momentum at the end because momentum is conserved, okay? It needs to be the same in the beginning as it is in the end. The value, the overall total value, okay? So that is where those equations come from. So here they give you an example problem. They say 2.0 kilogram, 2.0 times 10 to the 5 kilogram train is moving east at 21 meters per second with a 4 times 10 to the 5th kilogram loaded train initially at rest. Okay, so then in this case, your M1 would be this number, your V1 would be 21 meters per second, and moving east. So remember, we go east is to the right. So if it's moving east, this would be a positive 21. For your M2 would be the 4.0 times 10 to the 5th, but it tells you that it's initially at rest. Okay, if it's initially at rest, that means V2 would be 0, and this part right here would disappear. Okay, so if I erase, so let me not erase. So if this part right here, this whole thing would disappear. Okay, because V2 is 0 for that. Yeah, V2 is 0 for that train. What the question is asking is find the velocity of the two cars after the collision. So what we're looking for is this. We're looking for VF. Okay? So to find VF, you got to do some algebra. So what you would have to do is you would have to divide both sides by M1 plus M2. And you would get that VF, your VF, it's going to be a little hard to write, is equal to M1. In this case, it would be M1 times V1 I, okay? Remember, don't forget about the subscripts to I, okay? So the I is for initial, F is for final, divided by M1 plus M2, okay? And again, the reason this thing disappears right here is because it tells you the second train is at rest. Okay, so you plug the numbers in. M1 is this. Okay, that's your M1. V1I is 21, and it's positive because it tells you it's going east. And then you just have to plug in M1 and M2 at the bottom, where M1, again, is this piece, and your M2 is this piece. Plug those numbers in, and you will get 7.0 meters per second to the east. And does it make sense that when the first train runs into the second train, that it slows down? It should. Mentally, it should make sense. You have something that's moving running into something that is not moving. After they crash, you would expect the speed to go down a little bit. And it does. It goes from 21 down to 7. Now they're moving together because the momentum from the first train transferred to the second train, but now they're stuck together and they're moving together. But the velocity should definitely be less than it was in the beginning. If the velocity went up, then we would be missing something. That it wouldn't make logical sense. Hey, but you plug these numbers into this equation right here, and you get the 7 meters per second that they're talking about. Okay. So this piece right here, they're saying now calculate the kinetic energy of the two cars before and after, and they ask you was the kinetic energy if it was conserved. Remember the kinetic energy equation is 1/2 mass times velocity squared. Okay. So the reason they're bringing this up is because for inelastic collisions, momentum is conserved, but kinetic energy is not. Okay. The kinetic energy will not be the same. It won't. For inelastic or for elastic collisions, once you get to elastic collisions, the kinetic energy is conserved as well as the momentum. So for elastic collisions, both kinetic energy and momentum are both conserved, which is why they give you the example here of asking you to calculate it. So for inelastic, it's just momentum. For elastic, it's both. Okay. Kinetic energy remains the same and momentum remains the same. Okay, so in an inelastic collision, kinetic energy is going to be lost. It is converted into other forms of energy, such as either heat or it could be sound energy. Okay, some kinetic energy may remain after the collision or it may all be lost. It depends on the situation. All right. But in an inelastic collision, kinetic energy is not conserved. Momentum is conserved, kinetic energy is not. Okay. So here, this first equation, this is the same, it's the exact same thing for inelastic. This is the momentum. This is the momentum conservation equation. Okay. The left side again is your momentum in the beginning before the collision. The right side is your momentum after the collision, and they should equal one another. Okay. But with elastic collisions, you also have the bottom equation. The bottom equation is for kinetic energy. Okay. So what this is saying, again, the left side is, so I'm going to highlight it. The left side is the kinetic energy before the collision. And then the right side is your kinetic energy after the collision. Okay. And they should be equal to one another for elastic collisions. Again, remember the I is for initial, the F is for final. Okay. So both of those things are conserved for elastic collisions. And here they give you some examples. We'll look at these two, and then we'll go on to the assigned work. So here they're saying two billiard balls collide head on. As shown, which of the following final velocities satisfies the law of conservation of momentum? So this is focusing on this top equation right here. Okay, so note the mass of both balls is the same. So M1 and M2 are equal. And even though it says they collide head on, this is telling you that the velocity of the yellow ball is 0. So this ball is standing still. This ball is moving with 4 meters per second. It's saying which of these would satisfy this equation for the final and the initial. Okay. This is saying that all three of these answers would work. Okay. Why is that the case? Well, it's because if they have the same mass, this is 4. So we have the initial. It will be 4 and it will be 0. Whatever numbers you plug in here for the V1 final and the V2 final, as long as the velocities add up to 4, it'll be fine. So this is saying the final for ball A. I'm guessing the ball A is the one on the left and ball B is the one on the right. Notice how for all these answers, the numbers add up to 4. So in this case, this is saying that all the energy transfers to the one on the right. This one's saying some of them is transferred, but the numbers all add up to 4. So for the law of conservation of momentum, any of these numbers would work. But if you go to the next slide, since this is an elastic collision, it's saying which of these sets would satisfy the law of conservation of energy. And in this case, only one of them would work. And the only one that would work is the middle one. So this middle one would be your answer if you were asked to find what is the velocities of these two balls. You should be using these numbers. And the reason that is the case is because these are the only numbers that satisfy the bottom equation. So when you're solving for elastic collisions, whatever numbers you get, they need to work for both of these equations. Okay, it needs to work for both of those equations. So when you're doing the homework or whatever the assigned problems, and you're asked to find velocities and things for elastic collisions, just know that you have two options. Okay, you have the top equation and the bottom equation, and they may ask you to check your work with the bottom equation since it's a little more restrictive. But for the elastic collisions, you have two different sets of equations to work with. So again, inelastic, it's just momentum that is conserved. For elastic collisions, both of them are conserved. Okay, and they're just showing you a little diagram of what the collisions would look like. And then this is a little summary slide. All right. So now I want to go through some problems with you. I'm gonna go through the ones that don't have the keys with them, since the ones that do have the keys, you can use that for reference. Um, So this video is going to cover both day 5 and day 6 because they both focus on the same topics. So I'm gonna do number 8 and number 9 from the inelastic piece, and then I'm gonna do one problem from the elastic piece. So let's do number 8 here. So let's zoom in a bit, just a tiny bit. All right, cool. So number 8. Again, you guys have to learn to ignore the unnecessary information. So it says the white shark is the largest carnivorous fish in the world. That does not matter. So let's just focus on highlighting what does matter. It says the mass of the white shark can be as great as 3.0 times 10 to the 3. That looks like important information. That's going to be the mass of the shark. Boom. That's one thing we need to highlight. Okay, keep writing, blah, blah, blah. In spite of, or perhaps the mass is prize, so none of that matters. Okay. Suppose Joe is one of those fishers, goes on a cliff. Okay, it doesn't matter. This does matter. To see if the sharks are biting, Joe drops a. So here's another piece of information. This is telling us the mass of the fish. Okay. And let me make sure that I covered that up a little bit. That's going to give us, this is the mass of a fish that we're going to be using. It so happens, and so again, this is the mass of the shark, same as earlier. The shark sees the bait, which is sinking straight down. So here we have the velocity of the bait. So it's giving us the velocity of the bait here. That's important information. And it says the shark swims upward. So we have another piece of it. So we have 4 pieces of information here. Okay. So just focus on the information that's relevant. Don't get caught up in the story. All right. So we have the mass of the shark. We have the mass of the bait. We have the velocity of the bait. And we have the velocity of the shark. And what are we being asked to find? We are being asked, again, I always tell you guys, what is your final destination? We are looking for what is the velocity of the shark after it swallowed the bait. Okay, we're looking for the mass of the shark after it swallowed the bait. All right, so now let's organize this information. Okay, so we are doing number 8. Okay, so you always want to organize your information. What do we know? What did the problem tell us? So what are we given? What are we given, ladies and gentlemen? So I'm going to have S be for shark. Okay, so the S is for shark, just for labeling purposes. Okay, make life a little easier. S is for shark. And B is for bait. Okay. Okay. So we are given the mass of the shark. So I'm going to label that as MS. Mass of the shark. Well, let me use a different color because I have that labeled. I have that as red. So let's use a different color to make our lives a little easier. So MS, or the mass of the shark, is 3,000 kilograms. That's what we're told. 3,000 kg. That is the mass of our shark. Okay. The velocity of the shark in the beginning, so VSI, the initial velocity of the shark, is 1 meter per second. Okay. 1 meter per second. And be careful with your signs. Okay. So let's go back to the problem. The bait is falling where? It says the bait, which is sinking straight down. So the bait is going down. Remember, on graphs, we call down negative. Okay. The shark is swimming up. So because the shark is swimming up, we call that positive. So the shark has a velocity of +1. Let's go to the bait. If we start talking about the bait, the mass of the bait is 250 kilograms. Okay, let's fix that B. The mass of the bait is 250 kilograms. But the velocity of the bait in the beginning, VBI, is equal to negative. Okay, this is going to be -3 meters per second. And it's negative because the bait is going down. Okay, pay attention to the directions. Now we are asked to find the final velocity of the shark after it swallowed the bait. So we're doing inelastic collisions. Okay, this is what we're working with. So we need to work with our momentum equations. Let's go back to the slide. The first equation they show you is this one. Okay, you have your initial and you have your final. This is what we're working with. So we are looking for the final velocity. So let's split this up into two sections. Okay, you have your initial momentum. Okay, and we have your initial and you have your final. So our initial momentum. I'm going to just label that MOM for short. Okay, initial momentum. Our initial momentum is the mass of the shark. I'm going to just work in symbols for now. Okay, I'm not going to plug any numbers. I'm just going to work in symbols. So the initial momentum is the mass of the shark times the velocity of the shark in the beginning before the collision. Okay, the collision is, in this case, is the bite. The shark is going to bite the bait. Plus the mass of the bait times the velocity of the bait in the beginning. Okay, and that has to equal, okay, that has to equal your final momentum. I'm going to use a different color. Okay, that has to equal your final momentum. When you eat food, where does the food go? The food goes in your stomach. The mass doesn't just suddenly disappear. Okay, so now you weigh whatever you weighed before plus whatever food's in your stomach. So just like that, the shark is biting the bait. The new mass is going to be the mass of the shark plus now we have the mass of the bait because the shark ate the bait. The bait is in the stomach of the shark now. Okay, so just how it was in the slides. Okay, let me erase some of this so you can see everything. Okay, just how it was in the slides. You have the mass in the beginning, M1 V1 plus M2 V2. Now it's an inelastic collision. They stick together. Now it's the sum of both. Okay, so as long as this logically makes sense, that's the important part. Times whatever their final velocity is. Okay, so whatever their masses and speeds were in the beginning, it has to equal their masses times whatever their final velocity is. This is what we're looking for, okay? The VF, this right here is what we're trying to find, okay? This is what we're trying to find. So I need to get that by itself, okay? In order for me to get VF by itself, I need to divide by this, okay? So remember, to get rid of something, you need to do the opposite. Okay, you guys got to work on your algebra. So this is MS plus MB times VF. So these things are being multiplied together. So to get rid of something, you have to do the opposite. The opposite of multiplication is division. So I need to get rid of this by dividing. If I do that, I get that VF, my final equation is VF and I'm going to try to write small because I'm running out of space here. So VF is equal to MS VSI plus MB VBI, and that whole thing needs to be divided by MS plus MB, okay? And we have all those numbers. We have everything we need. We know MS. We know MS. We know VSI. We have that. It's 1. We know MB. It's 250. We know VBI. It's -3. And we know the bottom part too. Okay, so we have everything we need to answer this question. So now it's just about plug your numbers in. I'm going to change colors here. So just plug your numbers in. So MS is 3,000. So this would be 3,000. I got to write a little smaller. I'm running out of space. It's 3,000 times 1. Okay, it's 3,000 times 1. Plus, this is 250 times, again, this is -3, okay? Divided by, what is 3,000 plus 250? That would be 3,250. Okay? That's what you're plugging into your calculator. And if you plug that into your calculator, you should get that it equals to, I'm running out of space here, so I'm just going to put the final answer. You should get that it's equal to 0.69. Okay? Meters per second. And again, think about it logically. Does this number make sense? You have a shark swimming up. It bites some food. When it bites the food, it is now heavier. It is now heavier, so in theory, it should slow down. It was originally going 1 meter per second. It's now going basically 0.7. 0.7 is less than 1. This number makes sense. Okay. So that's number 8. Okay. Number 8, you just have to plug those numbers in and see what you got. Those were the steps. Okay. So now I'm going to erase all this and try to do number 9. Let's see if we can do it a little more efficiently here. So in number 9, what are we given in number 9? Number 9 is similar to number 8. I think we're looking for the same thing. So what are we given? We have a cow. Heaviest cow on record has a mass of this. So this is like important information. We have the mass of a cow. Okay, so we're going to need this. Lived in Maine at the beginning. The owner put the cow on a rail cart. And the mass of the cart is this. This is the mass of the cart. And pushes the cow to the left with a speed of 2 meters per second. Okay, so this is also important. Note the direction. It says the cow is going where? The cow and the cart are going to the left. We call left negative. So this would be a -2. And then we have another cow. That cow has a mass of this. Okay, so let's circle that. And it's on an identical cart. Okay, that's an important word. It says the cart is identical, which means whatever cart this cow is on, it's going to have the same mass as this one. And it pushes it towards the sage from the opposite direction. So if this cow is going left, that means this cow is going right. It says it's being pushed from the opposite direction, and this is the velocity that it's going. So the first cow is going to the left 2 meters per second, so it's a -2. The second cow is going to the right with 1.4, so it'll be a positive 1.4 meters per second. So now let's organize our information. I'm going to call the first cow, cow 1, and I'm going to call the second cow, cow 2. Okay? So I'm going to label that as M1 and M2. So what are we given here? So given, let's label this. This is what we are given. Let's change color here. We are told that M1, so cow 1, M1 is cow 1, it is equal to, that would be 2,267 kilograms. Now, I'm going to do something here, and I think you'll agree that it'll be easier. Now, these cows are moving inside of carts, okay? So for the sake of simplicity, I'm going to combine the cow's mass with the cart mass. So the cart weighs 500. So M1 would be the 2267 we got from the cow plus 500. So the total mass would be 2767, okay? So I'm just combining the cow's mass with the mass of the rail cart, since the cow is inside of the rail cart, okay? So this is the mass of cow 1 plus the car, okay? And then the second cow, weighs 1,800, so it's 1,800. Plus, it says it's it's the cow. The second cow is inside an identical cart, which means we're adding 500 again. And 1,800 plus 500 is going to be 2,300. Okay, so that's that. Kilograms. Okay. The velocity of the first cow, V1, V1I is going to be, again, it's going to the left, so it's going to be negative 2 meters per second. And then the velocity of the second cow is going to be positive, okay, positive 1.4 meters per second, okay? Why is that stuck there? That's interesting, okay? Meters per second, okay? So that's the mass of the cow plus the cart, mass of the second cow plus the cart, and that's the velocity of the first cow, and the velocity of the second cow. Okay, let's fix that a little bit too. We are being asked to find what is the velocity of the cows after the collision. So we are again looking for VF. Okay, we are looking for their final velocity after the collision. Let's set this up again in terms of momentum, because that's what we have to work with. So our initial momentum, okay, initial momentum, again, this is what we're working with. We're working with collisions. So we're going to be working with momentum. Our initial M-O-M, initial momentum. So our initial momentum is again going to be the first cow and its velocity plus the second cow times its velocity. And that has to equal our final momentum which is going to be, again, if you look at the problem, it clearly states the carts collide and stick together. Okay, if they collide and stick together, our mass is going to be the sum of both, okay? It is going to be the sum of both times whatever their final velocity is. This is what we're looking for. We are looking for, again, we are looking for VF. This is what we are trying to solve for. So I need to get that by itself. In order to get that by itself, I again need to divide by this. I need to divide by this to get rid of it because we're multiplying by it right now. To get rid of something, you need to do the opposite. So if I do that, I get, again, just working with symbols right now. It is always easiest to work with symbols first and plug the numbers in after. So we get that VF is equal to M1 V1I plus M2. Oops, it's an ugly M. That's an ugly M. Let's fix that. M2 V2I, all that divided by M1 plus M2. And again, forgive the sloppiness. It is super hard to write on this pad. So just plug your numbers in. What is our M1? Our M1 is 2767. And what is the velocity? The velocity, again, should be -2. Why is that? Okay, that's sliding with the screen. It shouldn't be sliding with the screen. Why is that sliding with the screen? Okay. No, just okay. All right, cool. All right. Yep, it's -2. So let's plug in our -2. Plus the second mass is going to be 2300. And I believe the velocity was 1.4. And again, that's a positive 1.4 because this is going to the right. The reason this is negative is because that one's going to the left. And this whole thing needs to be divided by 2300 plus 2767. If you do that, you get 5067. Okay, 2000 plus 2000 is 4. That'll be 47. That'll be 5. Yep, 5067. If you plug that into your calculator, you should get a value of -0.46 meters per second. Okay. Does this number make sense? You always want to think about that. When you get an answer, you want to think about, does the answer make sense? Which one of these is going faster? The one going to the left or the one going to the right? The one that's going faster is the one that's going to the left. Okay, so then now you got to look at the mass. Which one's heavier? The one's going to the left or the one that's going to the right? Again, it's the one that's going to the left. So the one that's going to the left is the heavier one and it's the faster one. So if that's the case, when they collide, the one going to the left is going to win. So your final velocity should be in that direction. And it is. We have a negative velocity, which means we're going to the left. But because of the collision, it should be less than what it was going originally. Originally, the velocity was -2, but now we dropped down to negative basically 0.5. So it won, which means that the momentum maintained that direction, but it's less than what it was originally, which what it's supposed to be. So this number does make sense. Okay, so when you're doing problems, you need to make sure that your numbers make sense. Okay, so think about it logically and try to rationalize your values or your numbers. Okay, so that was for inelastic collisions. Okay, that was for inelastic collisions. We're going to do one more problem from the elastic collision set, and we're going to do the last one, number 7. Okay, these tend to be organized by difficulty, which is why I do the last numbers, because the last numbers tend to be the hardest ones. Okay, so number 7 for elastic collisions. Let's see what we have here. Okay, so what information are we given? Let's scroll this up a little bit so we don't have that little gray highlight. We have 2 bumper cars. One bumper car is 25 kilograms. The other bumper car is 35 kilograms. Okay, let me not cover that. I'm covering it a little bit. We have some velocities. We have several velocities. Okay, so we have to be a little careful with this one. Things get a little more complicated for the elastic collisions. Okay. So this problem has two stages. So we're looking for the velocity of a car before the collision, and then we're being asked to verify it via kinetic energy. Okay, remember for elastic collisions, now you can work with both momentum and with kinetic energy. Okay, that's what we're working with here. So with that being the case, when it comes to elastic collisions, you need to organize your information just a little bit differently. Okay, so I'm going to organize this as given, again, like we always have in the last 2 problems, but I'm going to split it up this time into a before and an after, okay? And I'm going to try to do this as neatly as possible because space is not something we have a lot of here. So before. So when I say before, I mean before the collision, okay? So I'm going to call the first bumper car they mentioned bumper car number 1. Okay, so this right here is bumper car number 1. Okay, and then this right here is bumper car number 2. Okay, so this is bumper car 1, this is bumper car 2. So before, we are told that M1 is 25 kilograms. Okay, this is 25 kg. And V1I is 5. Is it positive or is it negative? It says that the car is traveling to the right. If it's traveling to the right, it should be positive. Okay. And then we are told that M2, which is the second bumper car, M2 is 35 kilograms. But we do not know its velocity. We do not know its velocity before the collision. We don't know what it is. This is actually what we're being asked to find. Okay, so I'm going to label that as a question mark. We don't know what this is. This is what we're looking for. Okay, so this is before the collision, and now we have after. Okay. So the masses remain the same. Okay. So M1 is again 25. That doesn't change. This is 25 kilograms. What does change is its velocity. That is an ugly G. So now V1, and I'm going to label this F now for final. So V1F is equal to, if I'm not mistaken, it should be 1.5 meters per second, yes. So this drops down to be 1.5 meters per second. And then M2, and the velocity doesn't change, or I mean the mass doesn't change. This is 35 kilograms. And the velocity, V2F, is equal to, they say it is 4.5 meters per second. Okay. Oh, I'm almost out of space here. That's no bueno. Let me see. Let me see if I can pull up, because I don't want to erase stuff. Yeah, let me open up Microsoft Word here so I can have something to work with, a blank sheet to work with. Okay. So I'm doing that just so I can have a blank little canvas to work with. So zoom in a little bit here. Okay. So this is our final before and after. This is the information we're given. Okay. Oh, I can't type here? Well, actually I can. Well, nope. I can't use the little pen thing there. I want to come up. It's interesting. Or do I have to be... Okay, I guess I have to exit. Or won't it lie? It really won't let me do it on here? Nope. Okay. All right. So I can't draw on Microsoft Word. I guess we're going to have to work with what we got. So hopefully I'm going to have to erase some stuff, but it's okay. So M1. Let's write out our momentum equation. So this is again going to be your final momentum and your initial momentum. So let me label that again. Start from the beginning, same way I have with the other problems. So this is our initial momentum. So remember, for elastic collisions, it will be the same for like the momentum is conserved. It's the same as inelastic. So this part isn't any different. Okay. So it's M1 V1I. Oh, it's getting a little complicated now. Plus M2 V2I. This has to equal your final momentum. And this video is getting kind of long now, so I'm actually going to speed this up a little bit. Okay, this has to equal your final. Okay. Okay, and again, your final. Now, this isn't inelastic, so they're not going to stick together. So there is no sticking together this time. So this is going to be M1 V1F plus M2 V2F. Okay. So I'm going to skip some algebra steps here. Okay, because you guys got to work on your algebra. What are we looking for? We are looking for the velocity of the second bumper car before the collision. So we're looking for V2I. In order to get V2I, you need to first subtract this part, the M1V1. You need to get it over here. And then after that, you need to divide by M2. And then that'll give you everything isolated. And because I'm running out of space, I actually have to erase this. I wish it would give me a bigger eraser. And if you do that, after you do the math, you end up getting that V2 is equal to V2I is equal to, after you plug everything in, you get M1 V1F plus M2 V2F minus M1 V1I, and then all that divided by M2. Okay? So you have all the information you need. You just have to plug everything into the calculator. That's all. So everything is up right here up above. You know M1, you know M2, you know V1I, you know V1F, and you know V2F. You just have to plug everything into your calculator. After you do that, if you plug everything in correctly, you are going to get that V2I is equal to, you're going to get 2 meters per second. Okay? You are going to get 2 meters per second. That is going to be your answer. Can I make this eraser any bigger? No, I can't. You're going to get that V2I is equal to 2 meters per second. Okay? I need this space to answer the last question. So now part B asks you to confirm your answer. So basically check your work. Check your work by using the kinetic energy equation. And then if you go back to the slides, the kinetic energy equation again is 1/2 times mass times velocity squared. Okay? So again, it's 1/2 times your mass times your velocity squared. Okay, for elastic collisions. Okay, it is the bottom part. 1/2 M1 V1I squared, so on and so forth. So if you plug everything in, okay, if you plug all of those numbers in, you're going to get that. I'm just going to go straight into plugging in the numbers. Okay, so 1/2 M1 V1I squared. So in this case, our M1, so this would be 1/2. Our M1 is 25. And then our V1 is 5. Okay, that plus 1/2 M2. Our M2 is 35. Parentheses, forgot the brackets. I'm trying to make this as neat as possible. This would be 35 times, what did we get? We got 2, right? No. For V1, yeah, V1 would be, yep, V1 would be 5, and this should be 2. Okay. Times, that's ugly 2. Times 2 squared. Okay. That's the beginning. And then this needs to equal, let's change colors here. 1/2 25. And our final velocity for mass 1 is 1.5. That's not a 15, it's a 1.5. Okay, so 1.5 plus 1/2 times 35 times 4.5. And that has to be squared. That's your velocity, okay? Again, that comes from the kinetic energy equation, which is that bottom piece right there, okay? You just plug the numbers in straight into that equation. If you do that, and you plug everything into your calculator, you should get that both sides are equal to 382.5, okay? You're going to get that 382.5 is equal to 382.5, okay? And because these numbers are equal, that means that the velocity that we calculated, the 2 meters per second, was correct, okay? Because in elastic collisions, kinetic energy is supposed to be conserved. And in this case, our kinetic energy is conserved. So this proves that our answer is correct. That's what part B is. Verify your answer by calculating the total kinetic energy. We did that, and it turns out we got the right answer. All right. So I know this is probably more math than you anticipated. It makes the fact that we aren't in class makes this a little more challenging. But just try to push through it. Do your best. If you have any questions, again, you can always reach out and ask. You can help each other out. If you need any more resources, I'll do my best to give you as many resources as I can. But you also have the internet at your disposal. Okay, there's plenty of videos, Khan Academy, things like that you can look at to help you out. Okay, but just do your best. Use the material as best as you can. Just go through these equations. Just follow the equations as best as you can. Okay, I know it's a little challenging, but challenges, help with growth. So I wish you all the best. Good luck. I hope you guys are all staying safe with everything going on. And hopefully we can get back to normal teaching soon. Okay, take care. I'll click. Can I? Yeah, there we go.